In this week's discussion, we are going to see more problems on network flow, and here's the first problem. So, assume that we have a set S of n people, and these people are traveling to a certain place in d days, and on each day I, there is a set Si, there is a subset Si of the S people, and those are the people who would travel. So not everyone is traveling on every day. We have a subset Si of everyone, and those are the people who travel on day I. And so now these people want to carpool, and so basically on each day I, one person is going to drive the rest of the people, one person from that set. So for example, if person 1 is in set Si, then person 1 could drive on day I. Now what we want to do is we want to find a schedule such that we assign to each day a driver, and that driver would carpool the rest of the people. And we have a condition on this scheduling, so we call a scheduling fair scheduling if each person drives at most delta I days, and delta I is defined here like this. So basically what it stands for, it's saying that for each day that the person wants to travel, they have a equal probability with the rest of the people to drive. So 1 over Si would show a equal probability of driving amongst everyone else on that day, and we sum it up over all the days that that person J is traveling. So this is some kind of an intuition behind what is happening for this quantity delta J. So now we call a scheduling fair scheduling if each person drives at most delta J, if each person J drives at most delta J days. And one thing is that we don't really need to schedule all days. It's possible that for some of these days we cannot find a driver. Well, technically this statement we show in part B that is not true, but for this part we don't enforce that we have drivers for all D days. But we want to find drivers for K days, for example, out of these D days, such that each person drives at most delta I days. So this is the scheduling problem that we are looking for. It's basically an allocation problem. We are allocating each driver to a day. So, okay, this is a problem. Now we want to solve this problem using network flow, and this is the network that we're considering. So, as usual of network flow problems, we have a set, we have a node S and a node T, source and sink, and we have N nodes for all the people that we have, and we have D nodes for all the days that we have. And the way we assign the edges of this network is that we set an edge from S to every person, an edge from every J to T, and between each I and J, I being a person, J being a day, we put an edge whenever I is traveling in that day J. Now for the capacity, for capacity of S to any I, we assign delta I, that quantity that we defined, and the rest of the capacities are going to be 1. And well, again, the intuition behind the network now is, well, eventually the flow of the maximal flow of the graph is going to represent the number of days that we assign a driver to, and we need only 1 driver per day, so that goes for this 1 here, capacity 1 here, and this capacity delta I here, it specifies that driver I is not going to drive more than delta I days. Okay. So as I said, what we want to show here is we want to say that if we find the max flow of this graph, it is going to be equivalent to a scheduling, to a fair scheduling of these people with the now, so in order to complete the proof, we need to prove this claim basically. So we're saying that whenever we have a fair scheduling that schedules k days to drivers, we have a max flow of k. So we want to say that there is a one-to-one correspondence between first scheduling k days or k drivers and an integral max flow of size k of this network that we define. Okay, I explained about how to go with the proof of this claim a little bit, but to be more concrete, so we need to prove two things. First, consider a fair scheduling of k people and show that we can build a flow of k in this graph. And then the other side that is that if we have a flow of k in this graph, we can interpret a scheduling of k drivers or k days in our scheduling problem. So first, let's assume that there exists a fair scheduling that schedules k people to k days. And the way we make the flow is that we will have a flow of 1 from each path Sijt whenever person I is driving on day j. So we have a flow of 1 from S to I to J to T whenever driver I is driving on day j. Now we need to show that this is well, first we have to show that this is a feasible flow, in that we are not violating any of the constraints capacities here. First of all, we said that each day has only one driver, so the capacities of this kind are not going to be violated because we're going to be sending at most a flow of 1, so that these are fine. For these, again, because for each day j we have only one driver, so there might be a couple of edges which go to this j, exactly Sj edges which go to this j, but only one of them is going to have capacity 1, the flow 1, because we are assigning one driver to each day. So from j to t is also going to be fine. Now it remains this kind of edges. But have in mind that we said that we have a fair scheduling, and in a fair scheduling, each person drives only at most delta I days. And so, if we decided that person I is driving, then that means that 1 has to be less than, so anyway, any number of days that this person is driving is going to be less than delta I. So the capacity, the flow that is going to go through this edge is also going to be fine. Okay. So here it goes on why this is a feasible flow, and also about the size of the flow. Now, have in mind that in the fair scheduling, we are assuming that we are assigning k days to drivers. So basically, if you consider this cut, the flow that is going to enter this cut is going to be k, because we assign k drivers here. And so the flow that goes to t is going to be also k, and so the flow of the whole graph, the flow that we defined, is going to be k. So we showed that for any fair scheduling of k days, we will have a flow of size k in the network. Now let's take a look at the other side. Let's assume that we have a flow of k, integral flow of k in this graph. So the way that we will build the scheduling is we will see which of these edges that goes from these days to t have capacity 1 and which of them have capacity 0. Flow 1 and flow 0. Those days would be the days that the drivers would be assigned to. And then when the flow of such an edge is 1, then that means that there is a edge here with flow 1 again. Again, I'm emphasizing that we are looking at integral flows. So these flows are going to be either 0 or 1, and so are these. So if we have a 1 here, then that means that there is an edge here going from days to people from this node that has flow, and that edge is going to show us the driver on that j, and that day j. Okay, and again, because we have this constraint delta I here and we found a feasible flow, then that means that no driver is driving on more than delta I days. So not only if you find a scheduling, it is also a fair scheduling. And so this concludes proof of claim here. And so in order to find the scheduling, we basically need to find a flow, or a max flow in this graph. And so we will have our scheduling. We can interpret our scheduling from the max flow that we find. Now let's take a look at the runtime of the algorithm we described. So our algorithm basically has 3 phases. The first phase is to construct the network. The second phase is to find the integral max flow in the network that we described, and the third part is interpreting this flow to a fair schedule. Okay, now let's see how much time does each of these phases take. Well, first for constructing the network, if you look at the network here, we'll see that, okay, we have n nodes here and d nodes here, and we have 2 nodes s and t. And well, the number of edges is, we have n edges here, we have d edges here, and we have at most n d edges here, right? So, well, if you sum all of these up and take the O of all of them, you will see that the size of the graph is going to be nd. So the time that it will take to build it is going to be also O of nd. Now, what we do is we find a max flow in this graph. We know that the time that it takes to find a max flow in a graph is E times F, where F is the size of the flow and E is the number of edges. So we said that the number of edges is ND. And we'll note here that we have D nodes here, each have an edge to T with capacity 1. So the maximum flow that this network can have is going to be D. And so here we have nd times d, O of nd squared is the time that this phase 2 takes. And for phase 3, basically what we do is we take a look at each of these nodes here, these edges here, and then we decide who is going to drive on which day. So again, this is going to take a time at most O of nd. Again, if you sum all of these up, you'll see that the time that it takes to run this algorithm is going to be O of nd squared. So this is the proof for part A of problem 1.